Welcome back. We're going to go through worksheet 1 in momentum here, starting off with number 1, Roman numeral 1 I should say, which is just the concept of what's going on. So let's get into it. If you throw a ball horizontally while standing on roller skates, you will roll backwards. Will you roll backwards if you go through the motions of throwing the ball, but still hold on to it and don't actually release it and throw it? Explain what happens during each of the steps through this motion. So whenever I do any problem with momentum in particular, but really this is kind of a general thing, I'm looking for like an action thing here. And so in this case, we know that our action is throwing something here. And so I'm looking at before and after this little action here. So I'm going to draw two different pictures here. One like before state, you might say, of what it's like at the beginning, and then one what's going on afterwards here. So in the before state, we got a person roller skating. So go ahead and draw somebody roller skating with me as best you can. This is going to be good. Top of their shoe and some roller skates. And have a ball in their hand. They're going to be having a good time because they're on roller skates and doing physics because everything is physics. Get a helmet on. Maybe get little elbow pads. Little knee pads on. That's a really high knee there. Looks like we got tumors. Okay, so they have some sort of ball in their hand, and this is before the action here, so they haven't thrown it yet. But it looks like in my picture they're probably going to throw it to the right-hand side. And I'll draw a similar picture on the right-hand side to speed things up here. I'm going to go ahead and just copy this thing over. And now in this one, they're going to be throwing it, or they will have already thrown it, I should say, to the right-hand side. So maybe I'll just take it out of their hand there, and we'll put it in the air here. And we'll see that it's kind of come from there already. And it's got some initial velocity at there. And so then it says that you will roll backwards. Well, I'll go ahead and put that here. So this is the person here has some then, well, maybe we'll call it a final velocity. We'll say that the initial velocity of this person here is 0. And then we'll say the initial velocity of the ball is 0. And they got some final velocities over here. Will they actually go backwards? That's a good question. If I pushed on something really hard and I wasn't able to push back on the ground there, maybe I should draw on the ground. Would I get pushed backwards? In this case, you're pushing that ball to the right. So imagine that the ball was like really heavy, not really light, but instead, what if the ball was like a car? Something that is on wheels, similar to a ball there. And I pushed really hard on that car, I would definitely feel a push going backwards there. So we're saying that if I put, and I want to kind of sketch that out there. If I put in this picture they can do it. If I put a force going on this ball here that way, then the ball is going to put a force on my hand there. So I'm going to start that force vector on the hand there, and it's going to put some force going backwards there. Now we know that this force and that force must be the exact same because this is the force on the ball by the person, and this is the force on the person by the ball. That sounds like a law there. That is Newton's third law. For every action, there's an equal and opposite reaction, or A acts on B, then B acts on A. And we've measured that in the lab before, that it's always the exact same amount of force. So I push something to the right-hand side, that's something that's going to push me to the left-hand side. Now, if I am on these like roller skates down here, so I can't like push against the ground here, horizontally anyways, it's obviously I'm pushing downwards on the ground. If I can't push horizontally on the ground there, now I have nothing that's going to oppose my motion going backwards. We're kind of assuming that this is going to be a frictionless case, or using our energy concepts, that there's not going to be any thermal energy from the deformation of these wheels or the ground there as well. Kind of simplify the situation. Just look at the before and after of just tossing this thing. So that means that, yeah, I will roll backwards. I will get pushed backwards. And if I have an unbalanced force on me, notice that if I am looking at the person here, let's do it for the person. If I'm looking at the person, I go and sum up the forces. And a lot of times I'm doing this in my head, but we'll go and do it without full. I see that I have some force here on the person by the ball. Force on the person by the ball, and that's an unbalanced force. I don't have any other forces horizontally here. We have forces vertically here, so we'll go ahead and put it in the X direction there. And that's going to the left there, so that's in the negative there for to the left. That's going to be equal to ma, therefore this thing, this person in this case, is going to be accelerating, again, to the left there in the X direction, the same direction as that force. Okay, so that does make sense that they will roll backwards there from a force perspective. What about for momentum? Well, that's a good question. Let's go ahead and let's get into it for this unit here then. Now notice that I have this nice little divider, so I can do my work both before on the left-hand side here and my work afterwards on the right-hand side over here. So now first let's go ahead and let's define our system. You can define our system in many, many different ways. Here we just did the acceleration then for the person because we made the system our person. And I could make the system just the person. I could make the system just the ball, or I could also make the system both the person and the ball. I'm going to go ahead and make my system both the person and the ball. So this is going to be separate from that little calculation there. So my system here is going to be the person and the ball. I specifically just made the system everything that's interacting here. Just that person and the ball. The ground is interacting, I would agree, but that's only vertically, and these things are moving horizontally. And I know that horizontal motion, vertical motion, they're completely separate from one another, so I'm not going to have to worry about that ground just holding me up there. And now if I make the system both the person and the ball, am I transferring any momentum outside of my system? What do I mean by that? I look at this and I go, hey, I'm pushing on the ball, and that's why the ball gets going, right? The ball has some motion now. Well, if the ball has extra motion going to the right after I do that, well then it forces me to go to the left, as we said here, is accelerating to the left. So then I gain some motion, but then going in the opposite direction. Okay, so like the ball got going because I forced it to get going, but then I got moving. I started rolling backwards because the ball forced me that way as well. Interesting. So now you could say I gave the ball motion. Great. But that's not the end of the story, is it? You can also say that the ball gave me some motion, gave you some motion, gave this person some motion, in this case going to the left in the opposite direction. Okay. So the only thing that's transferring motion, or pushing on one another horizontally in this case, is just the person and the ball, and so I made my system both of those objects there, everything that has momentum involved in this problem. All right, that means that I'm not transferring momentum outside of my system here. If you were thinking about it like an LOL diagram, no, we're not doing energy here, but you can still do the exact same idea here. If I was thinking about that, I would put the person and the ball in here. I am not doing this. I'm trying to draw an X through an arrow there. That's not too clear. I'm not transferring no transfer of momentum in or out of the system. In, out of system. Okay. Now, if that's true, and another way to say that is I look at these forces here, and there's no external force there as well. So kind of a parallel way to say this is that there's no external force on my system. Now you might say, well, that's not entirely true, because isn't the ground, we have the free body, if we drew the free body diagram full and complete for this person, we got the earth pulling the person down, as well as the earth pulling the ball down, and the ground supporting that person going up there as well. And I agree with that. However, we don't have any momentum up and down, nor are we changing our momentum up and down. So while there is that external force there, you know that both of those forces there are balanced, therefore not causing any changes in motion, therefore not causing any changes in momentum there. So that's why, so I'm kind of saying this, but really only in the X direction. Okay. So now if that's true, as we know from before, now I can see that my change in momentum for my system must be equal to 0, meaning that I'm transferring momentum maybe between the person and the ball, you might say, but I'm not transferring momentum in or out of the system, so my change momentum's got to be 0 for the system. So that means that, like, oh, at the beginning here, how much motion did I have? Well, they weren't moving, so my original momentum at the beginning there was a big fat 0. And that means that my momentum afterwards here must be 0 as well if I have a change momentum as 0. Well, how could that be? Because I have motion in the blue ball here, and I have motion in this person here. How could the motion be 0 at the end? Well, let's keep going and let's figure this one out. So if the change of momentum is 0 for the system, now I can just go, well, how do I find the change in anything? Well, it's just the ending momentum minus the beginning momentum is equal to 0. Well, let's go rearrange that, and then I can go, oh, the beginning momentum is equal to ending momentum, as we just said. Well, let's do that for each object. Well, each object I have the momentum of object, let's say P for person at the beginning, plus the momentum of the ball at the beginning there as well. And that's got to be equal to the momentum of the person afterwards, plus the momentum of the ball afterwards. Now let's think about this. We can go. We'll go ahead and let me do it like this. I know that all of these momenta is just the plural of momentum, is not equal to m times a. Hello, is equal to m times v. I know that this is a vector there, and that's a vector there, and mass doesn't have a direction to it, so it's a scalar quantity, non-vector. So, and I look at these, I go, okay, great. If it's got a direction to it, I need to be able to describe that direction to it. I need to be able to mathematically put that in, and we know direction of velocity can be positive or negative. We assume the standard Cartesian coordinate plane unless we state otherwise, and so we have the xy here, and I assume that it's positive here, and negative, and negative over there. And so then, well, let's think about the ball here. The ball is going to have positive or negative velocity. We look over here and go, oh, the ball's got positive velocity. Great. But that means that the person is going to have a negative velocity. So then, yeah, how does this right-hand side add up to be 0? Well, I know that this guy right here, when I go m times v for the person, plus m for the ball and velocity of the ball there, I know that this, let me do this in a different color here, I know that this guy is going to be a positive quantity. Clearly all the masses are positive, but this guy is going to be a negative quantity. Oh, so now we're hopefully starting to see how this right-hand side can add up to be 0, because I know that this bit is 0 and that bit is 0, because both of these velocities at the beginning were 0. And so now I have some motion in the ball, some positive motion, you might say, but then I have some equal and opposite motion, you might say, for the person. Now, does that mean that the person is going to be going the same speed as the ball? Well, you know, the velocity is not the only part of the equation. We also have these masses in here as well. Let's go ahead and let's draw these masses maybe size-wise. So I'm going to erase this mass here, and I'm going to ask you, hey, which mass is bigger, the person or the ball? Clearly the person, so this is going to have a huge mass here in comparison, and the ball's mass you would expect to be really small there. Okay, so now I know that this quantity is going to be negative, this first quantity is going to be negative, the second quantity is going to be positive, and they both have to add up to be the same thing because they have to add up to be equal to 0. So that means that here my velocity must be relatively small, and here my velocity must be relatively big, so that when I multiply the two quantities together, both the first term and the second term there, I get the exact same value, just positive and negative of one another. Oh, okay, all right. So that means that the velocity of the person, we can write this up to the side, I know that the velocity of the person, or you might say the speed of the person, let's not get into positive and negative bits there, but the speed of the person is going to be less than, and I might even say much less than the velocity, the speed, of the ball. And the double little absolute value lines are exactly that. They're just absolute value lines, and they're just saying take out direction there. Okay. And this, if you haven't seen the double less than or the double greater than sign, just means a lot less than, because we're probably assuming that the mass of the ball is a lot less than the mass of the person. Okay. Great. So that means that we will actually roll backwards there. And did we create momentum? Well, on first glance, you might say yeah, and I understand why you would say yes, because at the beginning, we didn't have something moving. We had nothing moving. And at the end, we had two things moving. So it sure seems like we created motion. However, because momentum is a vector there, and because momentum is dependent on velocity, and velocity has a direction there, momentum can be positive or negative, you might say. It can be pointing in different directions. So you can have the momentum of the ball be canceling out the momentum of the person, and you get a total amount of motion as zero. Right, because I have some bits moving to the left, some bits moving to the right. If I added all of those together and kind of took the average of everything in my system, which is the person and the ball, that would average out to be a motion of zero, zippo, nothing. Right, because they're kind of like going in opposite directions there. They're not kind of going, they are going in opposite directions. Cool. So that's that.